All right, here's a couple more Lewis dot structures, vsepr, angle, polarity, and IMF. Again, you don't need process for these, but if you don't get the Lewis dot structure that I got, make sure you go back and review how to do the process and the final Lewis dot structure so that you have it in case there's a process question on the test. P2, so right now I know it's going to be linear, 180 degrees, nonpolar, and dispersion. Okay, because I only have two atoms. So there's no central, so there's no lone pair. They're both the same. Two dots equal a line every single time. So really all I have to figure out is what's going to be in the center. And I know we need 2, 4, 6, 7, 8 for them to be happy. Phosphorus has 3 gaps, so it wants 3 bonds. N2H2. Okay, so again, nitrogen's going to share that responsibility of being in the center. Hydrogens are going to go on the outside. I'm going to single bond everything, and then I need to go back. Nitrogen wants to have 3 total bonds because he has 3 gaps, 1, 2, 3, 4, 5. So he wants 3 bonds. Well, I have 1 bond with the hydrogen. This guy can't be a double bond because hydrogen maxes out at 2 with its incomplete octet. So to get my 3rd bond, 1, 2, 3, I'm going to double bond the nitrogens. Okay, but wait, there's more. 1, 2, 3, 4, 5. Don't forget those lone pairs for valence electrons. So now if I were to check, my valences agree. 1, 2, 3, 4, 5 for the nitrogens and 1 for the hydrogen. And my octets agree. 2 max for the hydrogens, 2, 4, 6, 7, 8 for the nitrogens. Still check valence and octet, even though I'm not checking it here, to make sure that you're in a rhythm and so you don't make any silly mistakes, because you don't want to miss the lone pairs up here because that's going to throw off your vsepr, your angle, your polarity, and your IMF. That's a big whopping 0 out of 4 points on that problem. All right, so this is 2 lone pairs. So what do I have to do with that? Remember, split or 2 central atoms, not 2 lone pairs, 2 central atoms, split it in half, and we end up with 1, 2, and a 1. 1 lone pair and 2 atoms bonding with that nitrogen. The other nitrogen, 2 atoms bonding and 1 lone pair. So 2, 1 is going to be a bent. That's 117 degrees. He has lone pairs, so he's polar. He has fun bonds. So type of IMF is hydrogen bonding. C2F4. Okay, carbons are going to share, and we're going to spread around the 4 fluorines. Fluorines, remember, have 7 valence electrons, so they need 6 unbonded or 3 unbonded pairs. 1, 2, 3, and 1 bonded pair. Carbon, 1, 2, 3. Oh, he's not happy, so I'm going to up him with a 4. Now carbon, 2, 4, 6, 8. Now all our carbons have the correct valence and octet. Fluorines, correct valence and octet. Okay, now the outer atoms are the same. There's no lone pairs and it's symmetric, so non-polar for you. Okay, and that means he's mainly dispersion forces. And what's its structure? 1, 2, 3, trigonal planar, 120 on each carbon. Okay, or you could say that this is a beginning to be a linear bond of a long chain carbon. Okay, C2Br2, carbon center, bromines outside. Bromines get 6 in a single bond. Bromines get 6 in a single bond. Carbon wants a total of 4. 2, 4, 6, 8. Okay, this guy is all linear as opposed to the one before. This guy, there's no choice. It has to be linear, 180 degrees. Okay, he is all balanced, so again, he is non-polar, symmetric, no lone pairs, same outers. And since he's non-polar, he's going to have dispersion forces. Okay, C3H7, okay, 3 carbons. They're all going to share that center, so I'm just going to spread around the hydrogens. 1, 2, 3, 4, 5, 6, 7. And then we're going to leave the last for the oxygen and then the hydrogen. If you put this OH on any of the other spots, you are 100% correct because I did not tell you where it would go here. But if you tried to give hydrogen a double bond, your whole structure is wrong. Okay, your whole goal, hydrogen should only have single bonds. Carbon should each have 4 bonds. Oxygen should have 2 bonds. And then go back and check your valences. Carbon should have 4. Hydrogen should have 1. Oxygen, oh, see, this is why it's important to always check. Oxygen should have 6 valence electrons. So 2 unbonded pairs and then 2 bonded pairs for 2, 4, 6, 8. Okay, if you do not have those unbonded pairs on oxygen, your whole structure is wrong. This is a really long chain, so I'm still going to call it a long chain. Linear. When there's 2, you can do the split. If you have any more than 2 and it's a carbon chain, just go with linear and 180 degrees. Okay, this is polar because we have this oxygen here. We have different outer atoms. Okay, if we only had the structure to here, then nonpolar. But that oxygen is throwing it off. We have a lot more electrons on this side than that side. So he is polar. And because we do have a fun bond right here, we have an OH bond. Okay, remember, it can be HF, HO, or HN for the intra. And if that happens, then you have hydrogen bonding as the intermolecular force. Okay, last guy, H2O2. O can do double bonds, so he gets to be in the center. Hydrogen goes on the end. And oxygen needs to have 6 valence electrons. Okay. This guy absolutely has lone pairs. You are not going to call this linear. Okay. We have 2 atoms and 2 lone pairs on each oxygen. So each oxygen has a bent structure. 104.5 degrees, or you could say 105. I just knew that because this is a fun bond. So it is polar hydrogen bonding. And in real life, this guy is going to do lots of little twisty things because of those lone pairs. So you're going to have kind of an odd structure going on there. Okay, now so a review. If it is nonpolar, it is dispersion forces every single time. The more molecular weight you have or the more molar mass you have, the stronger the dispersion forces you have. If it is polar but no fun bonds, it is dipole-dipole. If it is polar with fun bonds, it is hydrogen bonding, which is the strongest of all the intermolecular forces, or the forces to hold the molecules together. Intermolecular forces, since it's between molecules, help with solubility and rules and with boiling point, melting point rules.